Let's begin looking at the intermolecular aldol reaction. Here we see we have a dialdehyde. Same conditions. We add some base, we add some heat, and it's going to give us our condensed aldol. So let's take a better look at what's going on here. So because these are two aldehydes, and you can see that the alpha carbons for both of them are the same, it does not matter which alpha hydrogen you take off. You could take off this one or this one, you get this same product. So in this mechanism, we grab the alpha proton, we generate our enolate, and we know our enolate's resonance stabilized. Now our enolate is going to come and attack the other aldehyde via intermolecular mechanism. And then you can see we form an alkoxide, we do a proton transfer. We then take off the alpha proton, form another enolate. The enolate comes in, collapses down, kicks off the OH in an E1CB mechanism to form our alpha beta unsaturated aldehyde. Right there, there's our product. Pretty slick. Now when you have a linear molecule, let's see here. So 1, 2, 3, 4, 5, 6. So let's draw ourselves a linear molecule. There we go. That's what I want. Please open. Thank you. Okay, there it is. And we know this guy's going to become our enolate. When it attacks like this, how do you know what size of ring you're going to make? And it's really straightforward. You find the nucleophile or the enolate, label that carbon 1. 1, 2, 3, 4, 5. So that's showing you that carbon 1 is attacking carbon 5. So that means we are going to have a 5-membered ring. And you just draw it. Okay? And then you label the carbons. 1, 2, 3, 4, 5. And then you go back to your linear version here, and you just make sure the connectivity is correct. We see that carbon 1 is attached to carbon 5. Is that the case? There's the bond right there. Done. But what else is attached to carbon 1? We see carbon 1 is attached to an aldehyde. This guy right there. So we just put it on. Now carbon 5 also has attached to it this piece. But following the red arrows, it shows that carbon 5 has a hydrogen and a O-. So that's how you look at the connectivity when you form a ring of any size. Now, you cannot form any ring size that you want. Intermolecular reactions that form a ring are typically only going to be 5-membered and 6-membered rings. And we learned in Orgo 1 that's because 5-membered and 6-membered rings are the most stable of all the rings that we have seen. So we can see this guy is not going to work, because if it did, you would look and find where the enolate would form, and you would see that it would form right here. And that would form a bond with that. And what size of ring would that be? Number the carbons. 1, 2, 3, 4. It would form a 4-membered ring shown there. So that's not going to work. And then this guy down here, we see that we would get an enolate there. It would come and attack like so. And what size of ring would it form? Just count the carbons. 1, 2, 4. It would form a 7-membered ring. That's clearly not 5 or 6, so it does not work. It's really that straightforward. So this gets a little, this is really cool too. So let's say we have this guy right here. Now what is this? Well, we see in the blue, that's a ketone, and in red, that's an aldehyde. Both the aldehyde and the ketone has alpha protons. And we can draw them in. There's an alpha proton on this carbon, that carbon, and that carbon. So the base has an opportunity to rip off 3. And each enolate that's formed, shown here, will form different products, all shown right here. Okay? Now we can clearly eliminate 2 of the 3 based off of what we know so well. Let's say, no, of the 3 choices right here, we can clearly eliminate this one on the top very first, just completely eliminate it, because we see that it's going to make a 7-membered ring. So that alpha proton, yes, it could form that enolate, but the enolate will not form the intermolecular aldol reaction because it forms a 7-membered ring. So that's just automatically out right from the start. Okay, but then when we compare these two, we see they're both 5-membered rings. So both, in theory, should be plausible and could be a really good product. But recall what I said about aldehydes and ketones. Which one's more reactive between the two? Hopefully you've all said aldehydes are more reactive than ketones. Okay. So what you want to do is have the enolate attack the aldehyde, shown here. Because the aldehyde is more reactive, we want the enolate to attack it. That's more probable. It's energetically more favorable. That's how it works. And so we can see that this is going to be our major product because the enolate is attacking the aldehyde. On the bottom down here, what we have is this enolate is now attacking the ketone. And ketones are not as reactive as aldehydes due to the steric. So you have that methyl group there that causes some problems. And so this, in theory, could happen, but very, very minor product, if any. So the one in the middle is the favored product. Okay. Do you see how when we describe and show you major products, there's a rationale behind why it's the major product? And so for intermolecular aldols, it's about enolates attacking aldehydes. We can also have aldol addition reactions with nitriles and nitro groups. Okay. Now the reason why this works is that if the nitrile has carbon or hydrogens on this carbon right here, it will work. And these hydrogens here are relatively acidic. So on the nitrile, this hydrogen's acidic, and on the nitro, these hydrogens are acidic, and you can see the pKa's. So these groups right here are analogous to when you look at an aldehyde with alpha protons. So this carbon right here, or these hydrogens right there, those are the alpha hydrogens, and it's analogous to this guy right here. So we could say that's kind of like the carbonyl carbon, and there's our alpha. All right. So the carbon-hydrogen bonds that are directly adjacent to this carbon here are going to be acidic. And so when you add a base to this nitrile here, or this nitro group, it's going to abstract one of these hydrogens and form an, I was about to call it an enolate, but it's really not an enolate. I really don't have a name for these guys right here, other than the conjugate base of the nitrile, or the conjugate base of the nitro group. Either way, you can see that there is a negative charge, electron rich, and then that will be able to react with itself. So let me show you what I mean by that. So here's some examples. So here's some examples that I want to show you. So I want to show you the mechanism for this reaction down here. Okay? And the mechanism that I'm showing you for the one that I just highlighted is the same for the reaction above. The only difference is that you have a nitrile group here and a nitro group there. The mechanism is all pretty much the same. Okay, so let's look at that. So let's say so there's our aldehyde, and here's our nitro group. So what we're going to do, the first thing is that our base is going to come, grab that proton, because we see that that hydrogen's acidic. Okay. And that's going to generate this species right here. And now that species is going to come and react with the aldehyde. And that's going to give us this intermediate here. And then we do a proton transfer. What do we have here? Our base abstracted a proton, right? Which now became a acid. So that's going to come here, grab that, and protonate it. So just a simple proton transfer Nothing too fancy. And there's our aldol product. Okay. Now what would happen if we added some heat to it? Well, let's first look at the difference between the two reactions on this slide. Here we have our alcohol still present. And the reason why that's still present is because there's no heat. But here you see that we've added some heat, not a lot, but enough that we get a condensation reaction. And that's why you see that double bond right there. Okay. But what would happen? So that's what you need to see right there, okay? Another reaction is a named reaction, which is called a Robinson annulation. And in a Robinson annulation, what you're doing is forming a 6-membered ring. All right. So you see how it's all color-coded where all of the pieces are coming from. Okay. So you take a ketone and treat it with a alpha-beta unsaturated carbonyl compound, and then you form a 6-membered ring. And we do that under basic conditions, and we add a little bit of heat, and this reaction goes fairly well. It has a decent yield. But isn't that a pretty cool structure that we can make? A 6-membered ring. So not only are we forming a carbon-carbon bond, but look how, excuse me, how many carbon-carbon bonds we're forming. We're forming 1, 2. It's pretty cool. Okay. And not only are we forming carbon-carbon bonds, but we're forming rings. And that's important because a lot of natural products and therapeutics are 6-membered, 5-membered rings. If you look at the cholesterol molecule and other steroids, they're a series of 5- and 6-membered rings. And this is really important. And if we can learn how to make these things, that's pretty cool. And it can benefit many people when we design these drugs. So let's take a look at the Robinson annulation mechanism. Okay, your textbook, if I recall correctly, does not have a, I'm looking at the book right now. Yeah, it does not have a detailed mechanism. So you're going to have to get that from me, and I'm going to show you how that works. Okay, this slide right here is just showing you not a detailed mechanism, it's showing you the main parts of it and how it works. But I want to show you with a little bit more detail. Before I show you the mechanism, I just want you to know the terminology here, that the Robinson annulation reaction, what you're doing is you're doing a conjugate addition. And we went over that in previous chapters. So Robinson annulation is simply a Michael reaction. Okay? And it's an intramolecular aldol condensation. So Robinson annulation is taking these two reactions that we have seen now and combined it. And it combines it by this mechanism that I'm going to show you right now. So what we have is the ketone, and we see that the ketone has at least one alpha proton. So the base is going to come and abstract that proton, forming the enolate. So there's our enolate plus water was made. Okay. The next step, we just take that enolate and then react it with the beta unsaturated ketone. So the enolate is going to attack the beta carbon. It's going to attack as the 1,4 addition. It's going to be a Michael addition. So we see it's going to attack like so. Those electrons go there, and those go on the oxygen. And my arrows today are struggling. And so now that makes us have this product right here. Okay. And we have water hanging around because it's right there. So the alkoxide is going to come and we will do a proton transfer to make this. And there we go. Okay. But what did we also regenerate? We regenerated our base. So that base is going to abstract one of these alpha protons to form an enolate. And there's our enolate now. Plus our water. So now we have an enolate. We have a carbonyl compound right here. So we can do an intermolecular aldol. Attack like so. And now what is going to happen there? What size of ring do we have? Well, we count. 1, 2, 3, 4, 5, 6. That's going to form a 6-membered ring. So we draw that. So we just draw a regular 6-membered ring. And we know that this carbon right here is carbon 6. And we know carbon 6 just formed a bond with carbon 1. So now we just number it, make sure it's all good. And then we double and triple check if we have everything. So we see at carbon 6 right here, we still have a single bonded O-. Okay. And on carbon 2, we still see that we have a double bonded oxygen. Okay, so let me put that in black. We just generated water again, so we will do another proton transfer step. Okay. But if you look at the conditions, let's see, there it is. Right there. Heat. So when we add heat, and what do we have on this side also? The base. when we have those conditions, we are going to find the alpha proton that is next to the carbon that has the alcohol on it. So yes, this is an alpha proton, and that's an alpha proton. But we are looking for the alpha proton that is adjacent from the alcohol, because we are going to use a E1CB mechanism here, in which the base is going to come and abstract that alpha proton, bring its double bond there, and kick off the OH. And now we have made our alpha beta unsaturated ketone. Voila, there it is. And that's how it happens. Now I want you to be able to look at this molecule right here and analyze it retrosynthetically and to see that you have this product, and tell me what two pieces did it come from. Okay. So what do you have to do? The first thing is that you see a six-membered ring, and that six-membered ring is an alpha-beta unsaturated compound. So your eye zooms in on that baby right there, and you're like, ooh, six-membered ring, alpha-beta unsaturated ketone. So that's probably a Robinson annulation. When you identify that, the first thing that you do is you identify the alpha and the beta, and you break that bond. Okay, so you break that bond. So let's draw it again here with the bond broken. And on that beta carbon, you simply just take that double bond right here and put an oxygen on it, like this. Okay? But we broke this bond at the alpha beta, so we still have this. Let me draw it a little bit more exaggerated here. Okay, so let's number this here. So if I numbered that carbon 1, 2, 3, 4, 5, we see it 1, 2, 3, 4, 5. Okay, you see that there? And for the alpha carbon that got broken off, you are going to add one extra hydrogen, because that carbon needs to have 4 bonds. Carbon 5 needs 4 bonds. It already has 2 hydrogens. It has a total of 3 hydrogens, right? So let me take that back. So we look at carbon 5 right here. How many hydrogens are on there right now? There's only 1. So you need to add 2 more. Okay? Just like that. Okay, got that so far? Then the next step is we have to break this bond right here. Okay? And what I'm looking at now is that this right here is an alpha carbon, right? And that would be beta. Carbon 2 is beta to the blue alpha. So we're going to break that bond. And what happens is that the alpha proton, or the alpha carbon right here, we just break the bond and leave it be. Okay? But this piece right here that has just been broken off, we're going to do something to it. We're going to take that beta carbon right there, okay, and put a double bond there, just like that. Okay. And there's the two pieces that you're going to need to make the product. So here's our product, and how if I gave you a product and I asked you to predict what are the starting materials, that's the process that you undertake. And there it is. Okay. Now in a Robinson annulation, there are two very important things that you must consider. When you look at your ketone, it has to have at least one alpha hydrogen. Okay? That's important. Has to have at least one alpha hydrogen. When you look at your alpha beta unsaturated carbonyl compound, the alpha hydrogen has to have at least two hydrogens. Okay? And those requirements are reflected when you go back to the mechanism. Okay? So I would highly suggest that you go back to the mechanism right here. Okay? And then ask yourself, why does the alpha beta unsaturated carbonyl compound need two hydrogens? So we have to identify it in our mechanism, and there it is right here. All right? So follow that piece throughout the whole mechanism and see why you need two hydrogens. Next is the ketone right here. Why does it need a alpha proton? If we go to the mechanism, well, we see right here, we need that ketone to form an enolate. So it needs an alpha proton in order for it to become an enolate. That makes sense. So what would be a good exercise for you is to take this molecule right here and go through that exercise with the retrosynthetic arrows and see that, and convince yourself that you can come to these two product or reactants right here. So remember, what's the first step when you look at this molecule right here retrosynthetically? You break this bond right there, because that's our alpha, that's our beta, and we're going to break that bond. That's your first step. Okay. Now in chapter or sections 11 and so forth, these This material I'm not going to cover because the book does a very good job at describing this. And I've already talked about it in my lecture. This is using retrosynthetic arrows to analyze what pieces you need. So if this is your product, how do you know you will figure out that those are the two pieces that you need to make that product. So I've gone through all of this with you already. Okay. So you don't need to worry about that take-home quiz. Okay. Don't worry about that. But if you want to, I'd highly recommend that you do it because it would be good practice for you. And if you want to do it and email it to me, I'll be glad to look over it. Here's another reaction that's big in protein chemistry. And I'm not going to go into too much detail about it, but it's something that I want you to be aware of. And it's called reductive amination, in which you can form your amine right here. Okay, so we've seen that reaction. So this is nothing new, this piece right here. We form our amine. What's a little different is it's called a reductive amination because now we add sodium borohydride, which is going to reduce the amine into an amine. And voila, we do this on proteins all the time because proteins have a N-terminal amine, which you will learn all about in biochemistry. And the N-terminal amine in proteins is a synthetic target where chemists can attach molecules to it. So we can take a protein and attach, let's say, a drug molecule or a poison, whatever we want. A molecule that we think will make our protein more active or better. All sorts of things. We can attach it to the N-terminal amine. And here's just another reducing agent called cyanoborohydride. Just another tool that you put in your toolbox. Nothing to stress out about. And then we don't need to worry about section 13, about these sugars and whatnot. You will learn that in biochemistry. So that is the end of this chapter. And as always, if you have any questions or concerns, please reach out. I'm more than happy to help.